I'm going to, as clearly follows from the title of my course, I'm going to speak about homogenization of non-local convolution type operators. With stochastic homogenization, it means somehow nothing. To be more precise, I should say it like homogenization of operator with random coefficients, random, stationary, statistically homogeneous. It's much more clear. So, but first I would like to introduce classical convolution type operators and say a few words about the possible applications where this operators come from, and some basic properties of very simple convolution type operators. So let me write homogenization, the title of the course, homogenization of convolution type operators with random coefficients. I think it will be more clear. Well, classical convolution type operators in homogeneous media has the following form. Let's first discuss such an operator in the whole space in Rd. So we live in Rd, D any number greater than, let's say, 2, the case of one-dimensional. It can be also considered, but it's less interesting. Okay, let's write greater or equal than 1, no problem. And we have an operator, Lu, which is equal to integral over Rd, A of x minus y, u of y minus u of x, d. Here we should write x, and we integrate over dy. That's the classical convolution type operators with pure convolution kernel, you see. And in the majority of applications, and also from it's natural from the mathematical point of view to assume that A is a positive function, non-negative function. Everywhere in the space, and that A is integrable function. And since very often this operator has a probabilistic meaning, it's natural to use a normalization that the integral of A is equal to 1. So we will assume that integral of A over Rd is equal to 1. And then under these two conditions, this operator defined a bounded operator. This integral defines a bounded operator from L2 in L2 of Rd. And for young participants here, it's a very good exercise to check that. Let me write it as a lemma. It's classical result. It can be found in the literature, but it's also a nice exercise to check that this operator is a bounded operator. L is a bounded operator. In L2 of R. Well, but where do these operators come from, and what are the possible applications? It's also an interesting question, especially in the modern time when we should write some grants and projects and justify the study of this topic or another topic. So in our case, there are several models. In fact, Елена Жижина in her course explained a lot about the so-called contact model and the density of population, which is the first correlation function. Its evolution is described in terms of such an operator. But let me just give you a very brief description for those of you who didn't attend the previous courses, that if we consider a population of plants, for example, then an offspring typically appears not at the same position where the parents are, but at some distance because of wind, because of bees and birds and so on. The seeds are typically spread in a certain area around the position of the parents. And then, if we consider such an evolution, then if we have originally some position of this plant, some density, we will assume that there are many of population consists of many species, of many elements, and each of them produce offsprings with this density. Of course, in this case, it is just at the probabilistic density, and at random time, distributed with Poissonian distribution, each parent produce an offspring. Then the evolution of this population is described in terms of a parabolic equation whose elliptic path is exactly this operator. It's well known in population models and in probability theory. So now the question is, what is typically in such problems we are interested in large time behavior of a population. Typically, we don't care about what happens in 1 minute, but we are interested. There are now many organizations like the Greenpeace and so on. They are interested in what happens with different population after a long time. And if we want to study this for a long time, of course, we should make a change of variable, which is diffusive change of variable, and also it's clear that population, this kind of population, so there are, I didn't mention, but there are models in porous media. Each time there is some non-local, when some phenomenon is such that it produces something at certain distance from the position where some reaction or some interaction happens, immediately we have this type of model. Sometimes nonlinear functionals. And what is important that typically, like in the case of partial differential equation, typically the media is not homogeneous. So in this operator, we should add a coefficient which describes the local characteristics of the media, so the media is not homogeneous. And in this case, we should write our operator as integral over Rd, a of x minus y, and then some function mu of xy, which describes the local characteristics of the media, in contrast with partial differential equation, which are local and where all the local characteristics are important only at a particular point. Here we have a point from which offspring jump, where the parents are, and characteristics of a point where it appears. So there are 2 points. So now the function which describes the local characteristic is a function of 2 arguments. And then as before, u of y minus u of x dy. And here we should write lu of x.
U is another arbitrary.
U is, yeah, okay. In particular, for instance, if we study a population of plants, of course, U should be a positive function. But No, mu, I'm going to give all the assumption. Mu is positive, of course. So in general, it should not break the positiveness of the kernel. And we will assume that uniform ellipticity are satisfied, so mu will belong to the interval which is separated from 0. Well, so now we have this operator, and we would like to study watch time behavior. And it is clear from homogenization theory of differential operators that if we do not assume any any type of shift in the variance of the coefficient, then there is no hope to have something interesting in the limit. For operator, even uniformly elliptic operator with just the generic coefficient, we cannot expect, after scaling, we cannot expect any good limit. So we need some version of shift invariance. The simplest one is periodicity, and more tricky ones are almost periodicity or stochastic homogeneity. And we will focus on the last case, on stochastic homogeneous coefficient. So later on, I will introduce all the necessary assumptions. But first, let me make a change of variable and write down the rescaled operator. So we, as we decided already, we want to consider watch time behavior. So we assume we introduce artificial parameter epsilon, which is a small parameter. Then we assume that time is large, which time is of order 1 over epsilon square. And then probability theory teaches us that in this case we should take to be consistent with the central limit theorem normalization. In this case, we should take the scaling of time with the coefficient epsilon. If time is scaled with coefficient 1 over epsilon square, then space argument should be scaled with the coefficient 1 over epsilon. So we make the change of variable t times epsilon square times t, x, epsilon x. So, well, I consider, thank you, we consider for a while the operator dt, u is equal to lu, because if we want to discuss central limit theorem, then after the scaling, of course, I will drop the time variable, but just if we want to be consistent with central limit theorem and we want to speak about watch time behavior, we should consider the corresponding evolution, parabolic equation. I would slightly violating the notation, I will call it parabolic. It's not classical elliptic operator, but still. Evolution. Well, and then it... L is non-negative definite, right. I will prove it, yeah.
But actually it's just standard adiabatic approximation quantum mechanics.
Yeah. There are many for pure convolution operator. It's operator well known. Yeah. And so after this change of variable, the new operator, and it's a simple exercise for young researchers here to check that after this transformation. Of course, if we have time, original time of order 1 over epsilon square, then new time will be of order 1. And that's our aim to work not on the growing time interval, but make changes in such a way that we deal with a fixed time interval. So new equation will be, after that, it takes the form dt u is equal to L epsilon u. And that's why I wanted to consider the evolution framework. Now we can write what L epsilon is. And L epsilon maybe, okay. I should apologize in advance. Sometimes epsilon will be upper index, sometimes low index. It's the same guy, but I'm never able to follow the convention if it's upper. So it will be integral over, first of all, the scaling coefficient d plus 2 integral over rd a of x minus y over epsilon mu of x over epsilon y over epsilon, and then of y minus u of x dy.
May I ask a question here?
Yes.
Seemingly, after you change the variables, the u and x, the arguments of the function u, should also be changed.
Yes.
There is some kind of trick here.
Right, but u is a test function. So
So the trick is you change the variables and consider test functions independent of epsilon.
Absolutely, as usually. In PD, for instance, if we think about PD homogenization theory, we do exactly the same. We study the evolution of some initial profile. In the operator, coefficient are rescaled, but initial condition doesn't rescale. Or right-hand side of the operator. That's the trick. We change the operator, but do not change other data. So that's the operator we are going to study. And probably you will be surprised with the coefficient d plus 2 here. Look, epsilon square, it's natural. When we make scaling change of time, then here second order derivative in time is multiplied by epsilon square. We divide to have coefficient 1 here. We obtain power 2 here. But what about d? D is just Jacobian. Since we integrate in y, and since the coefficient, partial coefficient are also rescaled, it gives another epsilon to power d, which is just Jacobian. So you can check that this is the correct normalization of the rescaled operator. Well, now I formulate conditions on the coefficient. Even if we don't have this parameter mu, and if we want to study the if we want to check if the central limit theorem applies or not to the to the process with generator defined by L. If those of you who are not familiar with probability theory can just forget about this. But what is important, that in order to have central limit theorem work, we should assume that A has a second moment. It's well known that if this condition is violated, then central limit theorem doesn't hold. So our condition are, as I said already, let me write it, assumptions. A of z is greater or equal than 0 for all z. Integral of A of z dz is equal to 1 over rd. In fact, instead of 1, we could write any other strictly positive constant. It will be the same. Then we want to apply variational method, in fact. So, and in the random case, symmetric case, it is much easier than non-symmetric case. In the non-symmetric case, till now, there are many generic non-symmetric cases, still open problem till now. But in the symmetric case, the problem is solved. And so we assume that A of z is equal to A of minus z. It's a part of the symmetry. We will have to assume also something about mu, symmetry of mu as well. But for A, we need this condition. So this condition 2, this condition 3. And it's well known that we need the second moment if we want to have the central limit theorem, and this gives us a hint that we should also impose this condition here. And we will see many times that this condition is indeed required. So, second moment. Condition which reads integral modulo z square of z dz is less than infinity, integral over RT. That's the conditions on A. And now conditions on mu. Uniform ellipticity. And from infinity, yeah. Probably I abuse a little bit the language, but I call it uniform ellipticity. Maybe it would be better to say uniform coercivity, but well, uniform ellipticity. Condition number 5. Let me write it here. Mu of x, y is less or equal than mu plus, greater or equal than mu minus, which is strictly greater than 0. So mu belongs to the interval mu minus mu plus, and this interval is well separated from 0. And the last condition, again, symmetry. Symmetry is here, and another, so y is equal to mu of yx. No, it will be random. Yeah, the simplest model. As I said already, we cannot hope to have some homogenization result if we do not assume some translation invariance. Translation invariance must be very tough one, like in the periodic case. Just the shift with certain period doesn't change coefficient at all. Or it might be in a weaker sense, quasi-periodic, almost periodic, or even statistically homogeneous. Statistically homogeneous means that the law of any finite dimensional distribution doesn't change with respect to the shift, yeah. But only the law. Of course, the realization themselves might change a lot. Well, that's a condition which are supposed to hold.
Here's another question about why is it ellipticity? For example, if we take mu is equal to 1 identically, and a is the Dirac delta function, just for example, then the operator is exactly 0.
Yeah.
Yeah. Well, why speak of ellipticity?
No, of course we assume that a is from L1. L should be a usual function. And then,
we have some,
then the second moment are non-trivial. It's always a positive. If L is a true L1 function, then second moment form always a positive definite matrix. And then, for instance, central limit theorem states that this will be the limit covariance. So the limit covariance will be Gaussian the limit process will be a Gaussian process with non-trivial correlation, positive definite. So we exclude this case when it's a delta function. And in a sense, this case is trivial, yeah. Well, now we proceed with some. What are we going to do now? Assumptions are given. I already explained that this operator is, for each fixed epsilon, this operator is bounded as operator in L2 of Rd. But of course, because of this large parameter, the norm, L2 norm of this operator, the norm of this operator as operator from L2 to L2 will grow as epsilon goes to 0. And now a question, what is the limit behavior of this operator? What is the limit as epsilon goes to 0? If it exists, and if it does, then how does it look like? Well, now there was already a question if this operator is non-negative definite or not. Maybe just to wake you up, I will give a very short and very easy proof of the fact that this operator is non-negative. I don't know if it's evident, I will skip it, but I think for at least for young people it will be useful to see the proof. So, okay. So very simple lemma. L epsilon is non-negative. In a sense that for any u from L2, non-positive, in fact, let me write it like this, minus L epsilon is non-negative. Same story as with the Laplacian. In fact, it's negative operator. Same thing here. Which means that L epsilon minus L epsilon u is greater or equal than 0 for any u from L2 of Rd. How do we prove it? Of course, we will prove it for epsilon equal to 1 because the scaling doesn't matter. So what do? We say that let's do the by definition minus. That's right. It's equivalent to prove that without that sign minus it will be less or equal than 0, of course. So we write Lu u. Now I write the definition of this. When I write the inner product without indication of the space, it means L2. It's commonly used agreement. Well, and then we have integral of a of x minus y, mu of xy, u of y minus u of x, times u dy, u of x dx. That's by the definition is just the inner product. Integral over Rd, integral over Rd, right? Now we just change the name of variable. We denote the new y by x, and we denote x by y. Then, of course, the integral doesn't change.
The proof is done.
Hmm?
The proof is almost done.
Yeah. So it's even to the same integral. I don't write the area of integration. It's always Rd. And then here we have a of y minus x, mu of yx, u of x minus u of y dx. Let me write it. U of y dx dy. Everything is real valued. I will not touch the complex Hilbert space. Only. Yeah. There will be some, but probably not today. Well, and now pay attention to the fact that here this one is symmetric, so it's the same function. This one is symmetric, it's the same function. So we obtain the same expression as here, but with the sign minus. U of x transformed to u of y is transformed to u of y, and this expression just change the sign. If we write u of y minus u of x, it will be the sign minus 1. So using this representation, So let me write it like this. Yes. And I should, please forgive me, but I will do it just like this. And now, since this function are the same, I take L u is equal to, I sum up these two expressions, and I obtain that it's equal to 1/2 with a sign minus integral a of x minus y mu of xy u of x minus u of y square dx dy. And I think now there is no doubt that this expression is.
Referring to Tatiana's question, should we have to recognize this for complex values as well, right? This property, that it is Hermitian symmetric. Right?
Yeah, it will also work for, if coefficients are real, then it doesn't matter. The same will work for complex coefficients, no problem. If coefficients are not real, then we should define what is positive phase, and we should be more careful. But I don't want to touch this point. Well, and this completes the proof. So what do we have? We have a family of symmetric bounded operators which are non-negative definite. Very good family. In particular, if we consider an equation minus L epsilon u plus m u is equal to f with positive m, then this equation is always solvable. Then m is, yes, f is L2, and m is a fixed number. Yeah, spectral parameter. Zero is the border of continuous spectrum of this operator. Okay, we assume that mu is not identically constant, then it's a border of continuous spectrum. So, of course, we should, like in the case of Laplacian in the whole space, we should make small spectral shift in order to have full posedness of this equation. So, u satisfies, and m is positive. We consider this equation, in other words, u is just a resolvent of this operator applied to function f. And then what we have, and it's straightforward consequence, for instance, of spectral theorem, that u epsilon in L2 is less or equal than 1 over m, comma f. A solution of this equation, we call it as u epsilon, I think it's clear, L2. So we have a uniformly bounded family of resolvents. And the question is, can we say something about the limit behavior of u epsilon? Of course, for the generic mu, we can say nothing. It's clear. You can imagine that it's like in the case of PD. If you assume that the family is uniformly elliptic, but do not assume any particular structure of the coefficient, then if you scale coefficient, you can have in the limit basically whatever you want. Still uniformly elliptic, but that will be the only property. So now, in the periodic case, this results, this problem by direct PD method with correctors was solved in our problem with Elena Rezhina, who is here now. And it's periodic case means that mu is periodic. Periodic case, I specify now mu of xy is periodic in x and y. So it's periodic with respect to both variables. That's we have the following result. U epsilon converge to U0. And U0 is the solution of the following problem. Divergence theta gradient U0 plus M U0 is equal to F, with the same F is the same M, and theta is a positive definite symmetric matrix. So that's the result. This matrix theta, as usually, it's not some average of some coefficients. It is constructed in terms of corrector. So later on, we will see how it works in the stochastic case. But this is just to say that the limit operator has a rather different structure. Look, we started with the family. What is interesting in this theory, if we compare it with the homogenization theory for the usual elliptical parabolic operators. In the case of differential operator, we start with a family of uniformly elliptic operators. And in the limit, we have uniformly elliptic operators. This type of operator doesn't change during the homogenization procedure. Here, we start with the collection of bounded operator, non-local operator. In the limit, we have unbounded operator with compact resolvent, and it is local. The fact that it is local can be guessed, in fact, easily, because we know that the central limit theorem holds in probability theory, and it gives us the idea that it should be local. But still, it's very interesting phenomenon that type of operator in the limit change. And it's getting of this form. And our goal in this course is to obtain similar result for the operator with random coefficients. And yes?
I'm trying to understand, if mu is identically 1, right, then there's
yes.
nothing to homogenize, right? Or still epsilon in A, right?
Still, yeah, and I can give you, it's very good, thank you for this question, it's a very good question. If mu is identically 1, still there is a non-trivial result, and let me just formulate it to make it clear. So, sorry?
Is it possible to describe theta?
Theta? In the generic periodic case, there is a construction, there are auxiliary equations. We should first construct some auxiliary periodic solution for the cell problem. And the limit matrix is constructed in terms of some auxiliary problem. So it's not an easy job. It's the only thing which I can say now without this additional construction, that it's a positive definite constant matrix. I didn't write it, but it's a constant matrix. But I will give an explicit formula in this case when mu is equal to 1. That's why this case is interesting, because in this case, if there is no mu, if mu is identically equal to 1, then I can immediately write down the formula for theta. So let me. It's NL2, yes. Thank you. G with this limit problem.
What sort of convergence you have?
Hmm?
Not operator type? Or
Operator type convergence is in progress with our colleagues.
check my conditions 1, 2, 3, 4.
Sorry?
Check our conditions 1, 2, 3, 4 in abstract scheme, my field, right?
Okay. Well, for remark, so if mu is identically 1, then this theorem holds with theta, then theta ij is equal to integral over Rd zi zj a of zd. And you can easily check, again, it's a good exercise for young researchers, that this matrix is positive definite. No 1/2. It will be just symmetric matrix. It will appear, the term appeared 2 times. No, it's.
Maybe we need some additional condition on A, that A is locally in this situation.
No. This will be sufficient. Just second moment. Just second moment. In this case, just second moment.
No, in this case, yes.
Yes. No. Well. But in this case, only these conditions. Yeah.
But for this statement.
Okay.
If I naively looked at L epsilon, right, with mu erased mu 1, right? L
Yeah.
epsilon, then if there was 1 over epsilon t, this guy would converge to delta function, right?
No, 1 over epsilon to power d, it will converge that to delta function. That's why in the limit we have.
Since, it's trying to, probably that's crude, but maybe right intuition, right? If you have there is something like delta prime appearing there, right? And then it distributes to the classical operator second order.
Yeah.
Delta double prime, right?
Yeah. Then look, it's almost delta function. So u of y will expand u of y in the vicinity about x to Taylor series. U of x are mutually cancelled. First order term disappear because of the symmetry. And we have second order term which gives exactly this. Yeah.
That's more or less what I was trying to
Yeah, exactly. I understood, yeah. I just rephrased what you said, yeah.